So in this part of the lecture, we'll talk about how to create a reentrant exception handler in RISC V. So first, let's talk about this concept of a reentrant exception handler. We say that a program is reentrant when you can start the program again when you are in the middle of the program. So the idea here is that you can leave the exceptions enabled while you are processing an exception. So you have the regular execution of the program, that was the user code, an exception happened, and all the process of transferring the execution to execute the exception handler took place. So when that process happens, exceptions are automatically disabled. The question now is, when will you re-enable the exceptions so that they can occur again? Will you re-enable in the very beginning of the exception handler, which means that the processing of the exception itself can be interrupted by another exception? Or will you keep exception disabled throughout the execution of the exception handler so that only when that exception has completely been handled, another one could occur? If you wanted to keep the exceptions enabled while we are processing the exceptions, what you need is a reentrant exception handler. And the main issue to build a reentrant exception handler is where you're going to save the value of the registers that you need to use while you are in the exception handler. Let's suppose that you have a data area that is reserved for the exception handler. If in that data area you create one word for each one of your registers, so you have one word for T0, one word for T1, one word for T2, etc. So you create this data structure where you can save the registers in that data structure, but you only have one place where you can save each register. Then you do not have a reentrant exception handler, because if when you start processing one exception, let's say that you save T0 in its place, if you were to re-enable exceptions and a second one would happen, you then save the T0 for that second one in the same place, and you lose the first one. So in order to have a reentrant exception handler, what you need to do is to have a separate area to save all the registers that you have to save for each time that the exception handler gets invoked. And the solution to do that is to have a stack. So it's not your usual stack, it's not the stack that's handled by your stack pointer. Let's call this stack a kernel stack. If you have a kernel stack, then you can also have a kernel stack pointer. So the kernel stack pointer does not exist as a register in RISC V, so you're going to pick one of the registers, anyone that you choose, and you're going to use that register as a kernel stack pointer. So there is a very careful programming that you need to do in the beginning of the exception handler to make sure that everything is set up properly before you start processing the exception. And what you need to do is to create the space in this kernel stack for all the registers that you're going to save while handle that exception. So I created this last year when we realized that there was this issue that the RISC V does not have a special area for the data for the exception handler. It does not have the temporary registers that the MIPS had. So the solution here in RISC V is quite different than what we used to do in the MIPS processor. So what the solution that we're going to do is to create a kernel stack in the kernel memory region. Now there is a difference here. The RISC V processor does not have kernel data, so I'm doing live editing here. I'll change this kernel data here to be just data, and I'll change this label here to be the iTrap data label. And the reason why I'm changing this is to make consistent with what we're going to do in your lab. So with this change now, what we have is that I have in my data area, I have an iTrap data label, and I have some space there. Let's say that I have 4,000 bytes. This is a space that will reserve for the use of the exception handler. And this is just to simulate what happens. In the real processor, what happens is a different mechanism that we have through the virtual memory system that will reserve some space for the exception handler. But in 229, we have not covered the virtual memory system yet when we are covering exceptions. That's why we are using this mechanism. It will simulate very closely what happens in the real RISC V. And let's say that I use KSP to be the address used for the kernel stack pointer. So I'm going to have the value of the kernel stack pointer stored somewhere in this space, so that every time that an exception handler is invoked, I can read that value and I know where I should set my kernel stack pointer to be. And what I'm going to do is I'm going to keep the value of that kernel stack pointer in my scratch register at all times. So in between exceptions, the scratch register will contain the value of the kernel stack pointer that the next exception should be using. So exceptions can only be enabled after the value in the scratch register is consistent with the state of the kernel stack in memory for that exception. So what I have to do when an exception happens, I go into the scratch register, I find out where is the top of the stack right now for my kernel stack. I make a plan for how much space I'm going to need for this handler. I change the value of the kernel stack pointer to this new value, and only when the S scratch register has this new value in place, I can re-enable exceptions. And I'm going to be able to re-enable the exceptions well before I finish executing the code for the exception that I currently handling. So one of the things that I also need to do is at the startup time of my computer, I need to initialize the value of the scratch register to be the initial value of the kernel stack. So when the kernel stack is empty, I have an address where the kernel stack is, and I'm gonna put that address into my scratch register. So here I have the CPU, and let's say that I have the registers T0, T1, T2, and T3, and they contain values that the CPU, the regular execution of the program needs those values. But in the exception handler, in order to do what the exception handler has to do, I'm going to have to use those registers. So I have to save them all, because remember, the normal register calling and saving and restoring conventions do not apply for exception handlers. All registers must be saved. Here is my memory. And I have that should be value instead of a value there. And here are the control and status registers, and I have my scratch register here. Let's say that my scratch register contains the address 0x8FFFECFC. So here's my in my data area, I have this space that I have reserved for my exception handler. It's called iTrap data because the exception handler is also called the trap handler. And let's say that the address of that space is, or that space is at that address that I'm showing on the screen. At the startup, before I start the execution of anything in my computer, I'm gonna do a read-write, atomic read-write between T0 and the register control start register 140. That's my scratch register. So I'm gonna exchange the value between T0 and the scratch register. So now scratch contains the value that was in T0, and T0 contains the value that was in the scratch. Next, I'm going to load the address of the iTrap data that I have reserved into T0. So T0 now I'm going to receive the address 0x2000-2018. And now I'm going to add 4 to T0 because I want the address to be the address before the beginning of this. So the top of the stack is the address immediately before that space, because the first thing that I'm going to do is to lower the value of the stack pointer before I do any use for it. And then I execute the exchange again. So that exchange again is again executing the same instruction. So executing the same instruction again will exchange those two values. And now I have that I do at startup. I only do it one time in the beginning of the execution of my computer. And now I do any other initialization tasks. And my scratch register now contains the address, contains the top of the stack pretty much. The stack is empty right now, so the top of the stack is the address immediately before the beginning of that space. Now, how do I update the scratch register when I enter the exception handler before I enable any exceptions? So this task that I'll do now has to be done very carefully because it has to happen before any other operations happen. So my KSP is right now at that address, and so my stack starts at that point. My handler will first do an exchange of the value of T0 with the scratch like before. Notice that I never lose in the value of T0. I just change in the two values. So now the top of my stack is actually in T0. And now let's say that I need to save one register. So what I'm going to do is to write the value of T1 into the stack. Okay, notice that I did not change the stack pointer yet because all exceptions are disabled at this point. So it's perfectly safe for me to do this. And then I'm going to add 16 to my to the value that I have in T0, and I'm going to write that into T1. So now T1 contains what I wanted to be my new top of the stack. And now what I'm going to do is to exchange the values in this way. That's why this atomic read-write instruction admits two registers. So what I'm going to do is I'm going to move the value that is current in CSR 140, that is the 42, into T0. And I'll move the value that's in T1 into the scratch register. So this is what happens. Okay, so I restore the value of T0, and now my KSP in the scratch register has moved, so I have that new space to use for my exception handler. And now my exceptions are enabled, but and the value of T1 has already been saved because it's already in the stack, so I can enable exceptions now. And I can proceed to save the registers. So now I'll save the registers that the handler we're going to use. Sorry for the misalignment in the scratch value there. I'm going to fix this slide in a minute. So now I can store the value of T0 into the handler, into the frame of this handler, and I can store the value of T2, and I can store the value of T3. And notice that this is going to happen with the exceptions enabled. So at this point, I could start another exception before saving these values, and everything will be fine, because this other exception will create a new frame for the values that that exception should save. And when that exception restores everything, I'm going to have the same values into the registers. And then I can now use the values in the handler. And then in the end, I need to restore the registers before exiting the handler. What I'm going to do in this case is I'm going to restore the registers to the values that they had. So I restore T0, and then I restore T1. So I'm restoring the old values that they had. This is just like the same thing that you do when you are writing a procedure. So I restore all the registers. And now I have to disable exceptions so that I can move the KSP back to where it was. I need to update. So for right now, the exceptions are disabled. And what I'm going to do now with the exception disabled, again, I will exchange the value of T0 with the S-scratch. I will add 16 to the S-scratch so that it goes back to the original value. And then I will exchange again between T0 and S-scratch. And by doing that, now S-scratch will point out that the stack is in that position. So this is a way that I came up to, and then I can enable exceptions and return. So the code to do this is here. And using this code, you're going to be able to do exactly what I did with a stack. But for the lab, we have decided that you do not need to build a reentrant exception handler. So you can have an exception handler that has all the exceptions disabled while we are processing exceptions. The reason for that is twofold. One is that building this stack is more complicated and could be challenging for some students. The other reason is that it is very difficult for us to test whether an exception handler is reentrant or not, because it's very hard for us to control the occurrence of the exceptions while testing your code. Therefore, for the lab, we decided that you can build this if you want to, and have a reentrant exception handler so that you can have the experience of building one, or you can do an exception handler that's not reentrant, which means that the exceptions are disabled throughout the time that you are handling an exception. And in that case, you can have a much simpler solution. You can simply create one location for each one of the registers in your space that's provided to you, and you don't need to implement a stack. So let me stop here, this part of the lecture.